welcome back. I'm moving right along with sound waves. Now, sound cannot travel or propagate through a vacuum like light can, but sound waves can only travel through a medium such as air. And why is this so? That's because this air is made up of matter, and sound causes the matter to vibrate, so it needs matter to vibrate for it to travel. They're produced by mechanical vibrations. Sound travels as a wave, referred to as progressive longitudinal. Sound gives interference and diffraction effects and is often believed to be a form of energy because of that. A longitudinal wave can be sent along a spring. How can this be done? Well, you get the spring and you just push one end back and forth. You can have it fixed at the other end, push it back and forth, and you would see the compressions and rarefactions actually coming about in that setup. When a spring is pushed in a back and forth motion, compressions where the coils are closer together and rarefactions where the coils are farther apart travel along the spring. This is demonstrated below. So we see the compressions, which is the darker section. See it right here. And the rarefactions. And remember, the compressions are like the crests, and the rarefactions are like the troughs. Now, in a longitudinal wave, the particles of the transmitting medium vibrate to and fro along the same line as that in which the wave is traveling, not at right angles to it as in a transverse wave. What is a transverse wave? Right, a wave in which what? A wave that is produced perpendicular to from whence it was propagated, right? So in a sound wave, the region of compression is at a slightly higher pressure due to the air molecules being pushed together, whereas the region of rarefaction is at a slightly lower pressure as the air molecules are farther apart. The wavelength of a longitudinal wave is the distance between the successive compressions or the distance between successive rarefactions. The amplitude is the maximum distance the vibrating particle travels from its undisturbed distance. A longitudinal wave may also be drawn as a transverse wave to show how the displacement of one vibrating particle at a certain distance along the wave varies with time. Such a graph is known as a displacement distance graph and is generated via a cathode ray oscilloscope. A greater frequency wave produces a sound of higher pitch. What type of sound would a low frequency produce? Definitely it would be lower sounding, more bass, right? So more bass, so low pitch. A greater amplitude wave gives a louder or higher volume, as you can see here. Frequencies below 20 Hz is referred to as infrasound. The human audible range for hearing is between 20 Hz to 20,000 Hz. Frequencies above 20,000 Hz is referred to as ultrasound. As one gets older, the upper limit gradually reduces to 16,000 Hz. And here we have the parts of the ear. You have the pinna, you have the external ear canal, then you have the tympanic membrane, which is known as the eardrum. And then the eardrum then affects three bones, which is known as the hammer, the anvil, and the stirrup. This then carries sound towards the cochlea, which is filled with liquid, and tiny hairs, which carry the sound further to the auditory nerve, which is attached to the brain for us to determine what we're listening to. Uses of ultrasound. Medicine, so that is where we hear about ultrasound the most in medicine. Also known as diagnostic imaging, ultrasound is used to view babies inside of the womb. It is also used to examine internal organs. Communication. Animals such as dolphins use ultrasound to communicate with each other. Measuring distance. Bats are nocturnal and blind. To judge how far they have to fly, they emit ultrasound which reflects echoes off of objects to assess their distance from it. Measuring distance. Now the depth sounding is the use of ultrasound by boat operators to determine the depth of an ocean floor based on the time it takes the ultrasound to reflect. Since the sound wave travels twice, then to find the distance of the bat from its prey or the boat from the ocean floor, the following equation will be used, where we say speed of sound is equal to twice the distance divided by time. Sound waves are reflected well from hard, flat surfaces such as walls or cliffs and obey the same laws of reflection as light. What are the laws of reflection of light? Correct. First law is the angle of incidence is equal to the angle of reflection. Second law, angle of incidence, the angle of reflection, and the normal all lie on the same plane. Reflected sound forms an echo. If a reflecting surface is nearer than 15 meters, the echo joins up with the original sound, which makes the sound seem prolonged, and this is called reverberation. What is often done to lessen reverberation in concert halls or movie theaters? You are correct. They carpet the entire area. The floors are carpeted, the chairs are plush, the walls are carpeted, the backdrop is carpeted, so that sound will be more absorbed instead of it hitting off of the walls, causing a horrible movie experience. Could you imagine watching a movie and everything's going, hey, 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 you, come. No, that's not a good movie experience. Now in air, the speed of sound is about 330 meters per second at 0 degrees Celsius. The speed of sound increases at higher temperatures. In steel, the speed of sound is 60,000 meters per second. So here we have it. Picture cooler air near the water's surface. Sound travels faster in warm air. Okay, so refraction, diffraction, and interference. When a sound wave enters a medium of different density, it changes speed and it undergoes refraction unless it strikes the boundary at a right angle. Why do you think distant sounds are often more audible at night than during the day? Well, for me, I would say that there are less obstacles at night. You don't have any bouncing happening. You don't have any bending of light. You don't have anything. So less obstacles mean a straighter travel for sound. If you have another answer for that, you could put it in the comments. Diffraction, longer wavelengths, lower frequency sounds are diffracted more than shorter wavelength, high frequency sounds. Interference, what would happen if you place two speakers half a meter away from each other? What would you hear? You would start to hear overlapping and maybe sometimes some kind of either you're going to hear it amplified or you're going to hear sounds getting cancelled out depending. So ultrasonic waves in industry are used to reveal flaws in welded joints. Also, holes of any shape or size are cut in glass and steel by ultrasonic drills. So we have a rocket is seen to burst in the sky and the bang is heard 10 seconds later. If the speed of sound is 330 meters per second, how far away is the exploding rocket? So we know that speed is equal to twice the distance times time. So speed, so we have the distance, so we're going to say distance is equal to st over 2, and that will give us now, what is the speed? 330 meters per second, 10 seconds over 2, and we're going to have 3300 over 2 meters equals to 1650. Now if I draw it, it says a rocket is seen to burst in the sky and the bang is heard 10 seconds later. So gone in the sky, is up, and the bang is heard 10 seconds later. So wait, so it didn't travel, the sound didn't travel twice, it only traveled once. So therefore we don't need to divide by 2. The sound, it went up and it went up into the air, a rocket, 10 seconds later. If the speed of sound is that, how far away is the exploding rocket? So the exploding rocket is actually 3,300 meters away, because the sound did not travel. So you see, a rocket is seen to burst in the sky and the bang is heard 10 seconds away. So if you're down here, and you hear it, so it didn't travel twice, it only traveled once. So the exploding rocket is 330 meters away. So we're not going to divide by 2. Okay? So the distance is 330 meters away. In a displacement time graph, 2 cycles of a wave occupy 0.4 seconds. What is the time period? 2 cycles of a wave, that's 1. And then this is another one. So this is 2 cycles, 0.4 seconds. So we're going to divide this by 2 and we get 0.2 seconds because the period is one crest and then a trough, right? We draw the line right through here. And so if this is 2 cycles, then 1 cycle will be half of this. So that will be 0.2 seconds. And the frequency would be the amount of waves produced in 1 second. So if one wave is produced in 0.2 seconds, how many waves are produced in 1 second? And so we divide 1 second by 0.2 seconds, so on, equals to 5 hertz. Right, so 5 hertz. You should get 333,300 meters and 5 hertz. So moving right along into musical notes. What is noise caused by? Exactly. Noise is caused by vibration of matter. So musical notes are made up of three properties: pitch, loudness, and quality. The pitch of a note depends on the frequency of the source of sound. A high-pitched note has a high frequency and a short wavelength. The frequency of middle C is 262 vibrations per second, or 262 Hertz, and that of upper C is 524 Hertz. That's twice what middle C is. Notes are an octave apart if the frequency of one is twice that of the other. So middle C and upper C are octaves, or are an octave apart. A note is louder when more sound energy enters our ears per second than before, and is caused by the source vibrating with a larger amplitude. What does the word source mean here? Yes, radio, television set, a child banging a pot on a spoon, so that's the source. Quality. Does the same note on different instruments sound the same or different? No, they don't. The difference in sound arises because no instruments except a tuning fork and a signal generator emits a pure note, meaning of one frequency. Notes consist of a main or fundamental frequency mixed with others called overtones, which are usually weaker and have frequencies that are exact multiples of the fundamental, like what we spoke about a while ago. Overtones of 262 Hz are 524, 786, and so on. So you just keep adding 262 each time. So what will be the next overtone? You just add 262 and you get 1048 Hz. The waveform of a note played near a microphone connected to an oscilloscope can be displayed on the screen. What is an oscilloscope? Basically, it's a device used to produce waveforms. It is. So notes produced by different devices can have the same frequency or pitch, but will have different quality or timbre. Let's do this on what does the loudness or the pitch of a sound depend on. So the loudness depends on amplitude and the pitch depends on frequency. Okay, so draw the waveform of a loud, low pitch note. So if we draw loud would have a high amplitude, high amplitude, but low pitch, meaning that it can be less waves, right? So like this, high, so they're going to be spaced apart. Soft, high pitch note. So soft means that you're going to have a low amplitude and they're going to be closer together. So let's go to something like that, right? So soft means amplitude. So sound, intensity of sound refers to amplitude, and pitch would be for frequency. So from there you just determine how your wave's gonna go. Now if the speed of sound is 340 meters per second, what is the wavelength of a note of frequency 340 Hertz? So we have the speed. So speed is equal to wavelength times frequency. And since we're gonna have speed and we have the frequency, wavelength will be equal to speed over frequency. For each of these, you can just divide 340 by the frequency given. So for 1, 340 1 over S, and then for 2, you can just say 340 M over S divided by 170 1 over S. Your answer can be in meters. So the first one will give you 1 meter, and the second one looks like it will give you 2 meters. Right? That's the wavelength right there. And for your homework, you're going to look up waveforms with a note produced by a tuning fork, a piano, and a violin. Alright, that's it. See you around for the third installment, which will start with light waves.